So we begin the meeting. Today's speaker is Ilja Gogić. I hope I'm saying it correctly. It's my pleasure to introduce Ilja. So we have, last summer we had a chance encounter at the airport, and now we have another one. So it's kind of the destiny for us. So my pleasure to introduce Ilja because I know him, and also because I'm interested also in matrix matter. So let's hear what he has to say about it. Please.
Thank you very much, Lina, and thank you thanks to Ivan for inviting me to speak on this nice seminar. So today's topic is about spectrum shrinking maps and nonlinear preservers of matrix algebras. Well, I will present some recent results which are based on a joint work with Alexandru Chirvasitu from Buffalo and Mateo Tomašević, who was my ex-doctoral student. Now he has his PhD. Okay, so let us first fix the notation. So A and B, let A and B be rings, or most often they will be just associative algebras. As we all know, the Jordan homomorphism is between A and B is an additive or a linear map phi from A to B, which satisfies this symmetric product rule. Of course, in case of rings, we only require additivity. In case of algebras, we also require linearity. And when the rings are or algebras are two-torsion free, which of course for algebras is the same when the underlying field has no characteristics too, this is equivalent that phi preserves the squares. So this theory of Jordan algebras and the Jordan homomorphisms, in fact, started by the work of Pascal Jordan in 1933 in the context of quantum mechanics. I will not define what the Jordan algebras are. Of course, this is no associative algebra seminar, so I guess most of us do know that. But what is important here that most relevant Jordan algebras arise from associative algebras under this symmetric product defined by x circ y is equal to xy plus yx. This is the standard product in the algebra. We know that, on the other hand, when talking about another class of non-associative algebras, which is namely Lie algebras, which always embed into associative algebras under the antisymmetric product defined by the commutator, the same is not true for Jordan algebras. They are Jordan algebras. We do not arise as algebras substructures of associative algebras, and these are called exceptional Jordan algebras. Okay, so what are the typical examples of Jordan homomorphisms? First of all, it is clear from the definition that all additive, so let us now focus on, for example, on algebras, so all linear multiplicative and anti-multiplicative maps are, of course, Jordan homomorphisms. They trivially preserve squares. More generally, we can take any unital algebra and P to be any centrally idempotent in A. And if we have two maps, phi and psi from A to A, for example, let's say that phi is an algebra endomorphism while the psi is the anti-endomorphism, then we can look their combination in terms of P, which is just the sum of P x maps to P phi of x plus 1 minus pi orthogonal projection times phi of x. And of course, because these are orthogonal projections, these define Jordan automorphism, which is in general not linear, nor anti-multiplicative. Not multiplicative, not anti-multiplicative. So one of the central problems in this theory of Jordan homomorphisms is to identify the conditions on rings or algebras A and B under which all typical, we assume that they are surjective Jordan homomorphism from A to B are either multiplicative or anti-multiplicative, or more generally can be expressed as a suitable combination of these two types like we had in this example. So let us just mention a brief historical overview. I will just mention the state-of-the-art results on this subject. First, we have a famous Jacobson-Ricard theorem, which says that every Jordan homomorphism from an arbitrary ring into an integral domain is either multiplicative or anti-multiplicative. Also, by the same authors in the same year, so we have the result that if R is a unital ring as any ring, then any Jordan homomorphism from the matrix ring M matrices with values in R to the S is the sum of a ring homomorphism and an anti-homomorphism. Then we also have a nice result by Herstein and Smiley, which says that every Jordan epimorphism from an arbitrary ring into a prime ring. So a prime ring is a ring which satisfies this simple condition that if two elements A and B multiply R into 0, that one of the elements must be 0. So every Jordan epimorphism from an arbitrary ring into a prime ring is either multiplicative or anti-multiplicative. So in particular, if we focus on the matrix algebra Mn of F, so n-time M matrices over a field F, direct consequence of Herstein theorem and together with this column-Noether characterization that's of automorphisms, that all automorphisms of Mn of F are inner, we get that. So first we get from Herstein theorem that any Jordan homomorphism and the more non-zero homomorphism of MNF is either multiplicative or anti-multiplicative. On the other hand, we know that all non-zero Jordan endomorphisms of MNF are inner, and we combine these two results, we get that all non-zero Jordan endomorphisms of the matrix algebra are either of the form conjugation of the identity or conjugation by the transpose with the composition of the transpose map. So these are all Jordan automorphisms of Mn of F. Of course, non-zero Jordan endomorphism must be automorphism. Okay. Also, the study of Jordan, the theory of Jordan homomorphism is very important in the theory of Banach algebras. So let us fix that A is a unital complex algebra, not a priori not necessarily Banach at the moment. And for any element A, we define the spectrum of the element A as a set of all scalars lambda such that lambda 1 minus A is not invertible in the algebra. So now we introduce some well-known definitions. Assume that phi is an arbitrary map between unital algebras. A priori, I do not assume neither linearity nor unitality, just an arbitrary map. And we say that phi first preserves invertibility, which means that the set of invertible elements is mapped into the set of invertible elements. So whenever A is invertible, the image phi of A is invertible. The stronger condition is that phi preserves invertibility in both directions, which means that for any A is invertible if and only if its image is invertible. Also, we say that phi is spectrum shrinking or shrinks the spectrum, which means that for any element A, the spectrum of the image is contained in the spectrum of the original. And similarly, we say that phi preserves the spectrum if for all elements A, the spectrum of the image equals to the spectrum of the original. What do we immediately see? So if we work with linear unital maps, so linearity plus unitality, meaning that identity is mapped to the identity, we see that immediately that phi preserves invertibility if and only if it is spectrum shrinking. Okay, this is easy from the definition of the spectrum. Also, phi preserves invertibility in both directions if and only if phi is spectrum preserving. Okay, so these two conditions for linear unital maps are the same. Spectrum shrinking the same as preserving invertibility, also spectrum preserving as preserving invertibility in both directions. Okay. It's easy to see and also well known that we have a Jordan homomorphism between unital algebras A and B. It certainly preserves invertibility, which by the previous condition is the same as preserve spectrum shrinking. Okay. And first, we now will call the standard Markov-Sperse theorem, which says that every linear unital invertibility preserving map on n times n matrices. I will now work mainly on complex matrices, so I will just write Mn, meaning M and C. So any linear unital invertibility preserving map on n times n complex matrices is either multiplicative or anti-multiplicative. And consequently, by the previous result, this means that it must be a Jordan automorphism of Mn, and we know how they do look. They are just a conjugation of identity or on composition with the transpose map. Okay. Also, we have the famous Gleason-Kahane-Velasquez theorem, which says that if we have a unital Banach algebra A, we have a linear functional, unital linear functional on A. If it preserves invertibility, then it must be multiplicative. So it is a character of Banach algebra. And the same is true if instead of C, we assume that B is any unital commutative semisimple Banach algebra, so the Jacobson radical is 0. And motivated by this result, we have the famous Kaplansky conjecture. I also like to call it Kaplansky conjecture. I'll explain very quickly why. So the original conjecture by Kaplansky is under which conditions on two algebras A and B is any surjective unital invertibility preserving map necessarily Jordan homomorphism. Okay, so more precisely, he asked for general algebras, but he surely meant under which conditions. And then Aupetit in the year 2000, so it is more than 30 years, established this concrete variant of the hypothesis or conjecture, which says as follows. So let's assume that we have two unital semisimple Banach algebras A and B, and let phi from A to B be any surjective unital linear invertibility preserving map. So we have surjectivity, unitality, invertibility preserving, and linearity. Then the conjecture says that phi must be a Jordan homomorphism. A very famous conjecture. So first of all, if we consider maps which satisfy the condition of Kaplansky-Aupetit conjecture, so if the map is spectrum, so it is invertibility preserving, linear, and unital. Recall that this is the same as it is spectrum shrinking. So this means that the spectral radius of phi of A is less or equal to the spectral radius of the original. Okay, and we have a general result that says that all maps satisfying the Kaplansky-Aupetit conditions must be continuous. This is general result that whenever B is semi-simple and we have a surjective unital linear map from A to B, for which preserves spectral radius up to a constant, meaning that there is a constant M such that the spectral radius satisfies this inequality, then this map must be continuous. This was proved. I remember this from Aupetit book on spectral theory from 1991. These maps are called spectrally bounded maps, and they are also very highly investigated. I will now talk briefly about the necessity of all conditions in Kaplansky-Aupetit conjecture. First, we have the following simple example by Russo, which shows that surjectivity is essential whenever the A is not equal to B. So let's consider the map from 2 times 2 matrices to 4 times 4 matrices defined by this. So phi of x is leave the diagonal intact, and on the upper right triangular, we act as x minus x transpose. Okay? What do we see for this simple map? So it is certainly unital, it is injective, and of course it is spectrum preserving. But it is not a Jordan homomorphism, because if we check the formula for Jordan homomorphism, so we check this difference from these two squares, we get in general non-zero matrix. So this simple example shows that we cannot in general drop surjectivity. Also, semi-simplicity is essential, which of course was first explicitly noticed by Aupetit, even if phi is a spectrum preserving bijection. So let us consider the following example, also as already mentioned by Aupetit. So consider a subalgebra A of 4 times 4 matrices, which consists of 4 block upper triangular matrices of the following form. So A, B, and C. On the lower left triangle is 0, where A, B, and C are 2 times 2 matrices. And what we now do? We leave the diagonal intact, and on B we act as a transpose. Okay, so we define phi exactly like this. We leave so A we leave intact, C transpose, and B we leave B intact. This is what I wanted to say. My apologies. This map is clearly unital, bijective. It is spectrum preserving, but it is not Jordan homomorphisms, because again, the difference from these two squares is in general non-zero matrix. Okay. Of course, the image is clearly this algebra is clearly not semi-simple. Okay. Well, this Kaplansky Aupetit conjecture, there are many results on and many work has been done on it, but only special cases has been so far has been done, and it is, well, interestingly enough, it is widely open. It is highly open even for sister algebras itself. So what is known? Well, first of all, it is known that the Kaplansky Aupetit conjecture has an affirmative answer whenever B, so the codomain algebra B, admits a separating family of finite dimensional reducible representations. Then we have also a famous result by Jafari and Sourour that the Kaplansky conjecture is true when A and B are algebras of bounded operators on some Banach spaces, under the additional assumption that phi is spectrum preserving, not only spectrum shrinking, but spectrum preserving. Okay. And later, well, in 2002, Šemrl also gave a more concise and shorter proof of this theorem. Then almost 10, also we have the following theorem by Aupetit and Mouton in 1944 that says that the conjecture is also true when the Sokol of B, which is the sum of all minimal left ideals, forms an essential ideal in the algebra B. Now, 10 years later, after the Jafari and Sourour theorem, Sourour managed to prove the Kaplansky Aupetit conjecture when A and B are again algebras of bounded operators on Banach spaces, but phi is bijective and spectrum shrinking. Okay. Now here, if you see, here is we assume here that it is spectrum preserving. Now he relaxed to be spectrum shrinking map, but also bijective. And finally, one of very important result by Aupetit in 2000, and then I will first mention what Aupetit done and then what the Chui and Hu done. So first, Aupetit proved the Kaplansky Aupetit conjecture when A and B are 4 Neumann algebras, and either phi is spectrum preserving or phi spectrum shrinking and bijective. Okay, under this is the famous Aupetit paper from 2000, and then 4 years later, Chu and Hu managed to generalize Aupetit theorem when O domain is a four-Neumann algebra. So B can be an arbitrary semisimple Banach algebra, phi is surjective and spectrum shrinking map. Okay, and as I mentioned, despite all this progress, the conjecture is highly non-trivial and unsolved for general sister algebras, even for some very important classes of algebras, I think like Kunz algebras and so on, simple sister algebras. Okay, what we know, are there any questions? So I'm just talking, but not really following so there's nothing in chat. Please, if there are any questions, do not hesitate to stop me. Okay. What is interesting that some authors, let us go back to original variant of Kaplansky conjecture. So if you remember, the conjecture asks when phi is surjective, unital, invertibility preserving linear map, which we know that it is the same as spectrum shrinking map, okay? And there are variants, the same conjecture, but when the map is spectrum preserving, which is of course stronger requirement. And these two conditions are not, although they look alike, they can be very different because the approach can be quite different. What I want to say is that if we have, for example, a result for spectrum preserving maps, can they be easily generalized to spectrum shrinking maps? Okay, and the literature indicates it is in general very non-trivial. Very non-trivial, because if you remember, spectrum shrinking for unital maps, this is invertibility preserving, spectrum preserving is in both directions. For example, if we analyze Sourour's paper we mentioned from the result from 1966, in comparison to original Jafarian-Sourour theorem, so when going from spectrum preserving variant for algebras, so bounded operating bounding spaces, to just spectrum shrinking variant, the techniques in Sourour's paper are much more intricate and longer, and they're heavily based on complex analysis. So, but this leads to the following question, so which we asked in our recent preprint, one very general question. So let's say that we have two matrix spaces X and Y, or operator domains, under which conditions are on X and Y are all continuous spectrum shrinking maps from X to Y, if they exist at all, automatically spectrum preserving. Okay? Under which conditions, so two matrix domain X and Y are all continuous. I do not assume linearity, but only continuity, are all continuous spectrum shrinking map automatically spectrum preserving. Okay? So now, first we will consider the simplest case of matrix algebras, but we will need to fix a notation to spell our first result. So given a subset L in Cn, by delta L, we will denote the subsets of L that consists of all elements with at least two different coordinates. We will naturally identify the symmetric group Sn with the n times n permutation matrices, so that Sn forms a subgroup of the general linear group GLN. We will assume that L is invariant under the action of Sn by conjugation, so that then Sn also naturally acts on the set of connected components in the delta difference. Okay, now we have L, and we also assume that we have V with subspace of the algebra Tn plus, just notation for the algebra n times strictly upper triangular matrices. And now we denote by TLV the space of all upper triangular matrices where the diagonal is in L and the strictly upper triangular is in V. Okay, so the set of all diagonal elements with elements in L plus elements from this upper triangular subspace. We contain that Tn plus. Okay, and now we have the following general result. It looks a bit technical, but I'll soon give concrete examples. So assume that we have a positive integer n, we have a close connected subgroup G of GLN, and we have, as before, a linear subset V of strictly upper triangular matrices and a subset L of Cn. Now we define Xn to be the set of all conjugations by elements of X with elements of the group G. And we have three additional assumptions. First, that the set that L minus delta L is dense in L. The second one, that L, as originally assumed, that L is invariant under the action of the symmetric group. And also the important condition is that isotropy groups of the connected components L minus delta L in the intersection of G with symmetric group act transitive on the set of, which we know the first n natural numbers, we just denote as usual by bracket n. Okay, so we assume again that this set difference is dense in L, that L is invariant of the action of Sn, and that isotropy groups of the connected components of L minus delta L are in G intersection with Sn are transitive on this set bracket n. Okay, now the statement is as follows. So choose an arbitrary m if, so the statement is as follows. So if there exists a continuous pattern shrinking map phi from Xn from this matrix domain to mm, so m is other integer. So the map, such continuous pattern shrinking map exists if and only if n divides n. Okay? And in this case, when n divides m, the spectrum is automatically preserved. Moreover, not the spectrum is preserved, but the characteristic polynomial is preserved. Okay? So whenever we have a map, continuous map from the matrix domain Xn defined by this to mm, this means that n divides m, and then the spectrum is in fact preserved. Okay, as I said, this is a little bit technical, but let us consider the concrete examples. Which spaces of Xn are covered by this theorem? Well, first of all, the matrix algebra Mn itself. The second is a general linear group. Third, the special linear group. Then the unitary group, also the set of n times n normal matrices, and it also holds for the set of diagonals, semisimple diagonalizable matrices in Mn, GLN, and SLN. Let us briefly explain, for example, choose the SLN and UN, how this theorem is applied, okay? So let us consider the group SLN. So these are all matrices with determinant 1. So how can we express them as in this as a space Xn? So it is the corresponding space V. We take the strict upper triangle, the space, the Tn plus itself. For the group G, we take GLN. Okay, and what is L? L is the set of tuples with product 1. Okay, and then SLN is just the conjugation of TLV under the group G. The only thing we need to check here for SLN is that the set difference L minus delta L is connected. This can be done, of course, explicitly by explicit calculation, but we can also, I think, invoke here a more general result, which says that whenever we have a connected complex algebraic variety and delta L is closed algebraic subset, then the set the difference is always connected, okay? And this clearly satisfies, this L clearly satisfies the conditions, okay? This is for SLN. For UN, okay, the unitary group UN, we express them again as at G of TLV. What is G? Now we take G to be unitary group, the full unitary group UN. We upper triangle, strictly upper triangle, so unitary matrices of our course are diagonal as well, so it must be 0. And for diagonal, we take Sn to the power, S1 to the power n, circle to the power of n. So what is then this set difference? So this is just the nth configuration space of S1. So the n tuples from S1 that all coordinates are different. What we showed is that, first of all, this configuration space is always disconnected whenever n is larger than 3, included as well. And also that the symmetric group Sn acts transitively on the space of connected components of this configuration space, and that isotropic groups are the conjugates of the group generated by this cycle. Intuitively, what this means? So we have n sets, the n points on the unit circle, which are different, and we look what are the connected components, which points correspond to each connected component. But what it means that we only if we rearrange them using the cycle. This means this, okay? And of course, this acts transitively on. And so the theorem holds for UN. Okay. Also, how do we get general spectrum preserving maps from the domain Xn to the MM when Mn divides n? So let's assume that n divides m, so m is the product R and n. And what the obvious classes of continuous preserving maps from Xn to Mn, which is of course the same as MR of Mn, are given in this simple form. So we just take pi. So we decompose this R as P plus Q, and then we take P copies of X, we take Q copies of transpose of X, and we just conjugate by some continuous function from Xn to GLN. Okay, this is broad class of spectrum preserving maps when dimensions are different. Not necessarily, they can be also the same. Okay, also let us look some non-examples. So the first non-example are Hermitian or self-adjoint matrices. So let Hn be the set of all n times n self-adjoint matrices. We know that the selection of any, so the selection, for example, maximum eigenvalue of X, which is real, of course, this makes sense, is continuous. So the map which assigns to given a self-adjoint matrix A its largest eigenvalue is continuous. So we have a continuous eigenvalue selection, and whenever we have a continuous eigenvalue selection, we can perform a general types of proper spectrum shrinking maps. Take any m and just multiply this maximum eigenvalue by identity matrix in Mn. Okay, and this maps then defines a continuous spectrum shrinking map, which is of course not spectrum preserving. Okay. So for n times n self-adjoint matrices, it fails theorem. It also fails for the group spatial unitary group. I include here the details, but perhaps it is we can skip this at the moment. What I wanted to say, so we have some example, we have some non-example. For example, one of the examples for general linear group. Let's take its complement. So the complement is, of course, the set of all singular matrices. So what happens here? So let us fix some n which is greater than 1 and any k between 1 and n strictly less than n. And when we define by this, so n upper less or equal to k, the set of all n times n matrices of rank at most k, and by single of n, the set of all n times n singular matrices, which is of course the same in our notation as this set, okay? So, is theorem true for these sets? The example is, well, no. Why is not? First of all, what do we see? If k is less or equal to n minus 1, so in our expression of spaces xn, the diagonal set L, because the rank is at most n minus 2, on the diagonal there must be at least two zeros. So two eigenvalues must always be 0. But this means that the difference L minus delta L is always empty. So it's certainly not dense in L. So this trivial fails. The only somewhat interesting case here is when k is equal to n minus 1, so we consider all the proper space of all singular matrices. So in this case, the components L minus delta L are given as following says. So they're all n tuples lambda 1 to lambda n, such that some fixed component lambda r is 0. So we have n connected components of these sets. And now we need to look the third condition about the transitivity action on isotropy groups. But the corresponding isotropy groups are the subgroups of Sn, which fixes the earth symbol. This group is, of course, isomorphic to Sn minus 1 is the same. And of course, these groups do not act transitively on n. So this suggests that the theorem should fail. And not only it fails for a singular method, it fails very, very spectacularly. Why is that? Because we can, for any k, we can always find, and for any m, we can always find continuous maps from the set of matrices of rank at most k to mn that strictly string the spectrum. And how do we get this type of examples? Very easily, because we fix any nilpotent matrix mn, an arbitrarily continuous function from matrices at rank at most k to c. Okay, for example, constant, whatever. And we defined this assignment. So it maps phi, it maps the matrix x to the f of x times n. This is clearly continuous. It is spectrum shrinking. Why? Because matrix is singular, there is always 0. And the nilpotent matrix, the spectrum is consists only of 0, okay? And this map is clearly spectrum shrinking, but not spectrum preserving, okay? So the natural question is now, okay, perhaps we need to add some additional condition to avoid this type of maps. These maps, of course, is highly non-injective. So we can now ask, okay, what if we add injectivity? Is then the theorem true? Well, the answer is, well, it depends heavily on dimensions. It depends heavily on dimensions. Because to prove such theorem, we needed to use the manifolds and also the algebraic variety and so on. I'll just state our main result for simplicity. I will just mention when n and m are equal. So we have the following result. If k, so the rank is parameterized by k, if k is greater than n over 2, then any continuous spectrum shrinking map phi from this matrix at rank at most k to mn, so we have the dichotomy. It either preserves the characteristic polynomial or it takes only nilpotent values, okay? Also, this map, so we have an injective, now we add injectivity. If we have injective continuous spectrum shrinking map from mn less or equal to k to mn, if either k is greater than n minus square n, or the image of phi is contained also in the set of matrices of rank at most k, then preserves characteristic polynomial and consequently preserves the spectrum. Okay. And very interestingly, well, result, at least for me, when we did this, that for any k, this is this dichotomy, for every k, we can always find a sufficiently, so if we fix a rank, we can always find a sufficiently large n for which then exists a real analytic embedding of matrices at most k, n times n matrices at most k, into the nilpotent n times n matrices, okay? We cannot map them continuously, only injectively continue, but we also have a real analytic embeddings, okay? And I mentioned here how we get these embeddings, but I think that it is not so important at the moment. Okay. Let us now turn to finite dimensional algebras. So far we covered Mn, we covered some Lie groups, matrix Lie groups, we covered singular matrices, and now let's consider arbitrary finite dimensional algebras. Here the important class of algebras will be the structural matrix algebras, which were originally introduced by Van Wyck. What is this? So first, we assume that we have a quasi-order row or set of 1 to n. What is a quasi-order? It is a reflexive and transitive binary relation. Using this relation, quasi-order, we define the associated structural matrix algebra as a subalgebra of Mn spanned by matrix units Aj correspond to the pairs Ij is in rho. Okay, so linear span of this matrix units parameterized by pairs in rho. This type of algebras are known as structural matrix algebra, and we know that by A sub rho. It is very easy to see that SMAs, structural matrix algebra, are precisely the subalgebra of n times n matrices that contain the algebra of diagonal matrices. What SMAs enjoy is the following important property that which is well known, the property which is well known to hold the whole matrix algebra Mn, that whenever we have an SMA A row and a commuting family of diagonalizable matrices, there always exists a similarity S in A row, which simultaneously diagonalizes all elements of F. So we can achieve simultaneous diagonalization with similarity in the algebra itself. Okay. Okay, and we have this result for general unital finite dimensional algebras. So assume that A and B are unital finite dimensional complex algebras, both equipped with unique Hausdorff vector topology. Because they are finite dimensional, they have the same finite sets of maximal ideals. Let mx of A be this. Pi maximal ideals, let B has, assume that B has Q maximal ideals. And for any pair A and J, we define the quantities that ky is the square root of the dimension of A over pi I, and similarly mj is the square root of m over qj. Of course, by Wedenberg structure theorem, these are positive integers. And we have the following result that A and B are arbitrarily finite dimensional complex algebras. There exists a continuous pattern shrinking map from A to B if and only if for all J from 1 to Q, the linear Diophantine equation of this form, I will not read it, has a non-negative integer solution. Okay, so there exists a continuous pattern shrinking map if and only if this the linear Diophantine equation, so the coefficients are these dimensions, so the variables are x, y, j's. So if and only if such map exists, if and only if we have a non-negative integer solution. Similarly, we have a similar result when there exists a continuous spectrum preserving map. It's dissimilar, but now with additional requirement that for any such solution, there also must exist some y, and for each I there is a j such that some component is positive, strictly positive, okay? And also C says that, so we are interested in automatic spectrum preservation. So if every continuous spectrum shrinking map from A to B is spectrum preserving, then this family of non-negative integer solution must satisfy that for each I there exists some j such that this is positive, and we managed to prove the converse when the domain, so when A is isomorphic to structural matrix algebra. At the moment, we do not know, is it true for arbitrary algebras? The key here is that we use explicitly the intrinsic diagonalization within SMAs, okay, which we do not have for general algebras. And trivial corollary is the following: when we have a continuous eigenvalue selection, so we face unital finite dimensional complex algebra, so now B is C, so M is equal to 1. So then, by the previous result, A admits a continuous eigenvalue selection if and only if A contains an ideal of codimension 1. Okay. Alina, can you please tell me how much time do I
Let me
have?
see. Yes, it's 16:46, so more or less.
So
a little
sure,
bit.
I should finish.
Do you think so?
No. So what is I should finish
I suppose
by...
we have maybe 10 minutes for discussion,
okay.
or 5 minutes.
Okay, so 10 minutes is okay
to discuss. I think so.
To finish the presentation.
10 minutes, maybe it's too much because it's
too
already...
much. Okay, I'll just keep this and just mention the following variant, non-linear variant of a Kaplansky variant, non-linear Kaplansky variants of problems. So first of them was done by Šemrl, which says that if n is greater or equal to 3, that any continuous map from anti-matrices to itself, preserving the commutativity and the spectrum, is a Jordan automorphism of Mn, and hence of the standard form. Okay. This result was first proved by Petek and Šemrl in 1999 with some additional assumptions, but this version was proved by Šemrl, obviously, by using the fundamental theory of projective geometry. Also, now looking with our result, we know that all continuous spectrum shrinking maps are spectrum preserving automatically. So the Šemrl's theorem can be also generalized. Instead of spectrum preserving, we only require that maps are spectrum shrinking. Okay, we have a similar result for upper triangular algebras done by Petek. So any continuous map preserving commutativity spectrum is Jordan homomorphism. And now I will skip this and just say what is the general problem here. What would be some perhaps nonlinear variant of Kaplansky, a Kaplansky conjecture? So assume that we have a subset of n times m matrices. The question is, under which conditions is every let's say injective is necessary continuous map from X to Mn, which preserves commutativity and spectrum, or only shrinks the spectrum? When can such map be extended to Jordan algebra generated by the set X? And this extension is Jordan homomorphism. Okay, so we have nonlinear domain X, and we have assumption that phi is continuous, preserves commutativity and spectrum, or shrinks the spectrum. The question is, when can this extend it to Jordan homomorphisms on the Jordan algebra generated by X? And I'll just take 2 minutes if I can to finish this. what do we know? For each types of spaces we know. First, we know for structural matrix algebras. So this is Mateo and I proved in our recent papers. We have the conditions for structural matrix algebras. Not always, but we have necessary and sufficient conditions. Okay. Also, we know that this can be done for all the spaces mentioned recently, like matrix algebra, which falls from Petr's result, then linear group, unitary group, normal matrices, and so on. We also have the affirmative answer for singular matrices. And this is it. So far we have done this, and we are not sure what is the general pattern, if can be any general pattern. Okay, this is only finite dimensional space, and for finite dimensional cases, the results are highly dependent on the topology. Okay, there is very much topology involved in this type of results. Of course, I'll tell you about this at the moment. I think it's quite enough to stop here.
So thank you very much for the nice talk. And so it's time for questions. Does anyone have a question or a remark? Well, I have one. I am curious. You did a lot of very nice things with spaces of matrices, and I've been thinking about, did you a special kind of subalgebra of matrix algebras? I was thinking about, for example, Lie subalgebras of Mn. Do you have any results?
We haven't done this at the moment.
No.
What we have done is, for looking at this problem, so we have answers for this type of spaces I mentioned. So matrix algebra, we have GLN, UN, SLN, normal matrices, diagonalism matrices within. We have SMAs, structural matrix algebras, singular matrices. But of course, this is a natural question. Of course, another natural question is general Jordan algebras and so on.
Right.
Jordan subalgebras of Mn.
Right.
Lie subalgebras of Mn. So this is all very
open,
natural to ask.
Yeah. So I was thinking about trace zero matrices.
Sure. Well, we know the answer for trace zero. Yes, but for general, it has to be done. Yeah.
Okay.
Also, well, I would mention that this makes sense for infinite dimensional spaces as well.
Right.
Of course, and this does not seem to be easy.
Right. Okay. So, any comments, questions? So, if not, it
There's
remains
a comment in the chat.
Oh, sorry, I didn't see. Sorry.
I didn't see it. Okay, page 16. The non-example reminds me the IEP. Sorry, what is IEP? Okay, perhaps.
No. Any more questions? Oh, there's someone here.
Also, could you refer to the work of Diana? Sorry, which work do you think Diana, perhaps, is Diana here?
Yes, I'm here. I think that this IEP means inverse eigenvalue problem.
So that was something that I was talking about last week. So maybe we can discuss that at the department.
Yes. Yes. Do you see, Diana, what is the question? Can you, or we can
Well,
discuss?
at this point, I don't see the connection. Maybe I'm not, this is the first time that I see these results, but maybe this is a good idea to think more about these things and maybe possible connections between
Yeah,
our
sure.
work.
While organizing Alps Adria seminar, perhaps.
Yeah. Okay.
Thank you.
I don't see any more comments in the chat. Okay, so if there's nothing else, thank you very much for the interesting talk, and see you one of these days.
Thank you very much for listening to me.
Bye bye.
Bye bye.